Hello and welcome back to the Pre-Calculus 171 series given by Jeremy Lane, the instructor. And in this video, we're going to discuss the composition of functions. Now, given two functions, f and g, the composition of two functions is defined as f open circle g of x, which can be rewritten as f of g of x. The domain of f composed with g is the set of all numbers x in the domain of g, such that g of x is in the domain of f. And what that means is that you have two things to check. You have to make sure that you can put values into g first, and then whatever comes out of g has to go into f without causing any problems. So only values that satisfy both of those conditions are allowed to go all the way through the composition. So here's a little diagram of what I mean. So here we have an assembly line, if you will, where we have x being sent into the g rule, and then whatever comes out of g is then sent into the f rule, and what comes out of that is written as f of g of x. So when you're finding domains, the domain of g is this first gate, so x has to pass through that. If it doesn't go into g, it can't go all the way down. So any value x that goes into the g function will output some value g of x. The domain of f is the second gate, and what that means is that whatever comes out of g has to be able to go into f, okay? And when that occurs, then you're able to go all the way through, and any value that makes it all the way through is in the domain of f composed with g. So let's find some compositions. So suppose let's let f of x equal the square root of x and g of x equal the reciprocal of x minus 1, or 1 over x minus 1. So let's find the following. We have f composed with g of x, we have g composed with f of x, we have f composed with f of x, and we have g composed with g of x. So our first example, sometimes it's a little bit easier to track if we perform what is called a double substitution. We substitute g into f like any variable, and then we replace g with its own rule. So here we have f composed with g of x, and we just use the notation and say, hey, we have f of g of x. Now f rule, remember, is the square root. So I'm taking the square root of g, whatever the g rule is. And then I go ahead and say, but the g rule is 1 over x minus 1. So I make a substitution for that rule, and I get the result of the square root of 1 divided by x minus 1. So here's what I mean by a double substitution. Treat g like a variable when you put it into f, and then replace every g with its own rule. For example B, we reverse the order of the composition, and this time we put f into g. So wherever we had an x in the g rule, we put f in its place. So we end up with 1 divided by f minus 1. But f, remember, has its own rule. F is the square root of x. So I replace f with square root x, and I get 1 over the square root of x minus 1. Now, one important thing to notice here is that composition is not a commutative operator. In other words, you cannot switch the order of the functions in a composition and get the same result. So it's not like addition or multiplication where you can switch the numbers around and the sum will be the same or the product will be the same. Composition is not a commutative operator. It is possible to compose a function with itself, and this type of operation is usually referred to as an iterated function. So we apply f to the input multiple times, and we have f composed with f of x, or f of x. Now remember, f is the square root rule in our example, so we have the square root of f. So here we have the square root of x. Now fortunately for us, the square root of the square root can be rewritten as the fourth root of x. So this is known as an iterated function. I keep applying the same rule to whatever comes out over and over again. And here we have an iterated function now with g. So here I use the double substitution idea. I'm putting g composed with g of x, or g of g of x, g of x. And now I put g in for x wherever I see it in the rule. So this is 1 divided by g minus 1. Now, right away, we already know that g of x can't be equal to 1. If it is, I divide by 0. So then I replace the g with its own rule, 1 divided by x minus 1. And in this case, I still have that g can't be 1. And now with the addition of adding that g in there, I now have that x can't be 1, because if I put 1 in, I get a 0 divisor in the bottom of this fraction right here. I get 0 there. So I can't have 1 in. Now, doing some arithmetic, we notice that if I put x equal 2 in this spot right here, I'm going to have 2 minus 1, which is 1. And then I have 1 minus 1, which is 0. And that makes 0 in the bottom of this big fraction. So x can't be 2. I still carry the restriction that x can't be 1, right? So the x equal 1 restriction comes from the original, the innermost g function. And then with g of x not equal to 1, that's what I mean when the result of applying g can't go into the next function in the assembly line. And I find that occurs when x equals 2. If x equals 2 in the original g rule, then I get g coming out to be 1, which won't go into the next application of g. So here I have x can't be 2 and x can't be 1. Otherwise, I run into problems in my assembly line. Now, doing some simplifying here, I realize that when I have 1 divided by a fraction, I can flip that fraction over. And I get x minus 1 divided by 2 minus x. When I do this simplifying, the restriction that x can't be 1 apparently is lost. All right. And this is incorrect. The correct domain for this composition is that x can't be 1 and x can't be 2. So when we start simplifying these functions down, these compositions, we may lose track of a restriction, like as demonstrated here. But the domain must be tracked at each step along the way. So to simplify an expression, the components must exist at every step. So just because I employ the flip rule to simplify this other fraction down, to simplify this fraction down, let me see if I can grab it, there we go. Simplify this fraction down, I had to use the flip rule to get to this fraction. Now that looks like we might lose the x equal 1 restriction because now it's on the top. But that's not the case. X still can't be 1 because it has to work for every single step in the simplifying. Remember, each one of these is equal. So I don't lose restrictions as I simplify. In fact, I gain restrictions only. Either I keep them the same or I gain them. I never lose a restriction. Once a restriction is imposed through simplifying the arithmetic, I cannot lose it. Now here's a demonstration on how to get the components of a composition. So instead, we already know the end result, but now we want to figure out what pieces will give us that end result. So for example, find functions f and g such that f composed with g would be equal to 4 divided by x plus 2. Now there's many possibilities to choose from for f and g. Recognizing the order of the operations to being performed and deciding where to divide the rules into 2 separate functions is key. So what I did here is I listed out what I'm doing to x in the order it's done. So first I add 2 to x, then I take the reciprocal of that, and then I multiply by 4. So essentially, I can divide this set of operations up at any one of these places and take one of those rules to be an f rule and another one to take a g rule. So non-trivial choices for f and g could be any one of these. I say non-trivial because if you choose g of x to be x or f of x to be x, the identities, then there's no splitting apart. All 3 of these operations would be in just one of those rules, where the other rule would just be the identity. So we're talking about non-trivial choices for f and g here, stuff where you're not just using the identity. So for one of them, I chose g to be the x plus 2, and then I chose f to be the reciprocal of x multiplied by 4. And when I do the composition of f circle g, I get what the composition should result in. So this is one choice for f and g. If I choose g to be 1 over x plus 2, and then I choose f to be 4x, then again, I get the same result. So in this first example here, this one right here, I chose to divide these operations between the add to and the take reciprocal. This is where my division occurred. So I used the first step as the G rule, and the rest of it I grouped into the F rule. On the second choice, I did the division after I took the reciprocal, okay? So among my operations here, I used the first two to be the G, and then I took the last one to be the F rule. And that's just one way that you can go ahead and figure out which rule gets which operations so that you can build a composition. These are, I would say, simple choices. With more complex rules and more complex functions and more complex compositions, it may be slightly more difficult to do this. But for simple rules like add and take the reciprocal and multiply, it's pretty, you have a choice here as far as how you want to group these operations together to form functions. So determining the domain of a composition. We've already seen one example of this where we would have to compose and track the domain at each and every step of the simplifying. That is one way to do it. But another way that seems to be a little bit more applicable and more natural, if you will, is to go ahead and follow these 4 steps. And one is to determine the domain of G. The second would be to determine the domain of F. Now notice the order here, F composed with G. Determine the solutions to G equal to values not allowed into F. These are the values to exclude because these are the ones that break the assembly line trying to go into F. Remember, you have to go all the way through, all right? Then step 4, consider the intersection of the sets from step 1 and step 3 to determine the domain of the composition. So if we scroll back to the beginning where we had our picture here, this kind of outlined what we needed to do. The domain of G is our first gate, so we have to make sure we can go into that. The domain of F is our second gate. Whatever comes out of G has to be allowed into F. This is where we get that solving step. So the first step is to figure out what you can start off the machinery with, what you can put into G. The second step is to figure out what can go into the second part here. And then the third step is to say, is there anything that comes out of G that may not be allowed into F? And you solve those equations or inequalities. And then after that, whatever you start composing things and you go through and say, these are the values that are allowed all the way through, okay? It's a 4-step process. It reverts back to things we've discussed before, finding domains, solving equations and inequalities, things like that. So this is an alternative. It's very applicable, 4 steps, just all the time. And in many cases, this seems to be like more natural. The tracking your domain as you simplify may not be as applicable. It may not feel as natural, which is why I propose these 4 steps. Okay, so suppose f of x is 1 over x minus 1 and g of x is the square root of x. Find the domain of f composed with g. So if step 1, find the domain of g. Well, g is the square root of x. I'm allowed to put anything non-negative in. Find the domain of f. Well, I'm not allowed to divide by 0, so I have to exclude the value of 1. Now, is it possible for g to output a 1? Okay, can the square root of x ever be equal to 1? And the answer is yes. So we have to solve this equation. And what we find is that if the square root of x is equal to 1, that means that x has to be 1. Now remember, the values of step 3 are the ones to exclude, because these are the ones that break the machinery on the second application of the function. Now we consider the intersection of the results from step 1 and step 3. So x from step 1 says that I'm allowed to use any x value that's greater than or equal to 0. I have to intersect this with any x value that's not equal to 1, because I have to exclude the 1 that resulted from step 3. And the intersection of these two is simply the set of x's greater than or equal to 0, but not equal to 1. And written in interval notation, it looks like this: 0 to 1, union 1 to infinity. Thank you for your time and attention.